Yes, so I have to apologize because there was a shuffling in the program because I arrived yesterday and I switched with Omer, and I will give the higher order Fourier this talk on Sunday because of this. Sorry for that. It's yeah, I forget about that, sorry. But so the thing is that the two talks are somewhat connected because in the other talk, in the limits of functions on abelian groups, I will also introduce a limit concept for functions on abelian groups. And it's very interesting, by the way, there the limit objects are functions on measurable functions on Neal manifolds, which is an interesting topic. So, but now I am starting with ordinary graph limits. And this is a joint work. Most of this talk is a joint work with László Lovász. Some of these results were obtained when I was at Microsoft, when I was a postdoc at Microsoft. And Oded Schramm was there. And I have lots of very interesting discussion also with him. So, so let me start. So graph theory in general is just too general. So it is meaningful to divide it into sub-theories in the following way. There is the theory of dense graphs, which is substantially different from the theory of sparse graphs. I call a graph dense if the number of edges is roughly n squared, c times n squared. And the tools that you want to use in that case are very different from the tools that you want to use in the sparse case. When the number of edges, there is the bounded degree case, which is the other end of the spectrum, where you have c times n edges, and let's say that the degrees are bounded. And then of course, there are the cases in between, which a little bit less is known about that. And let me explain the difference between these two ends of the spectrum. So the main difference is the random sampling, which is natural to use in the two different situations. So if you have a sparse graph, let's say you have a bounded degree graph, then the most natural sampling process is to pick a random vertex v uniformly at random, and then you look at the neighborhood of v of radius k, which is, since the graph has a bounded degree, it will be a bounded object depending on the radius k. On the other hand, in the dense case, this sampling process doesn't give you anything interesting, because if you pick a random vertex and then you look at the neighborhood of radius 2, already most likely you get the whole graph, so it won't be a bounded object. You want to use a different sampling process where you pick k random vertices independently, and then you look at the induced subgraph. By the way, a remark: if you happen to pick the same vertex twice, don't worry about it. You double it and you don't connect them with an edge or something like that. So you always get a random graph distribution on k labeled points. Now, there is a big similarity. In both cases, the sampling process that I denote by sk. So sk of g is the sample distribution, is a probability distribution. These sampling processes are forming an inverse system. So if you have a k sample, you can recover the k minus 1 sample from that by just forgetting, simply forgetting. If you pick k random vertices, you look at the induced subgraph, and then you can just forget about the k's vertex. You get the distribution on the k minus 1. You get the sampling process sk minus 1. Similarly, in the sparse case, if you look at a neighborhood of radius k, then you forget the points of distance k from the root, then you get the sampling process k minus 1. So this is already a similarity between the two cases. And for this reason, let me introduce this language, which is very convenient. This is really just a language that I'm going to use. So let G be a family of discrete structures or just structures. Doesn't matter. And let us define a sequence of topological spaces. Usually these are compact topological spaces that I call the sampling spaces, which are forming an inverse system. So there is a factor. The arrows are continuous maps between the topological spaces, and they are factor maps between these topological spaces. So factor map is just a factor. If you have a topological space, you can take a factor space of it. And that's so okay, the thing is that if you have a partition of a topological space, then there is an induced topology on that partition. And the map from the original topological space to this, where you map each point to the partition set containing the point, this is a factor map. So, okay, I will give you examples. Okay, that will make it more clear. I just want to clarify this context, which I think once you understand it, it's very clean and very simple. So don't be scared. So there are these spaces that I call the sampling spaces, and they are forming an inverse system. And for every k, I introduce a sampling process in every concrete example, which is a Borel probability distribution on xk. But in a way that these probability distributions are compatible with the inverse system of the spaces. What does that mean? If you have a probability distribution on xk, that induces naturally a probability distribution on xk minus 1, since it is a factor of xk. So there is a natural induced map on the probability distributions. And so I look at sampling processes which are compatible with the factor maps. They are also, the probability distributions are forming an inverse system in a similar way. Okay, and in this general framework, I say that a sequence of objects F1, F2, and so on from G is convergent if for every fixed sampling process, Sk, the distributions Sk, F1, Sk, F2 converge in the weak topology. What does that mean? Here is the definition. A sequence of probability measures on a compact space C is weakly convergent if the integrals of every continuous function according to these measures converge. So you can take, if you have the above situation, you can introduce the closure of G with respect to this topology, with respect to this convergence notion. And the good news is that because it's done, it's introduced in that way, it makes sense to talk about the sampling from the limit objects. The limit objects are the elements of the closure of G. So you can consider the inverse limit of the topological spaces with respect to that system of arrows, and also the inverse limit of the probability distributions, and that will be a probability distribution on the inverse limit of the spaces. And this is what I call the general limit object. But if you get scared, I show you 5 examples, and it will be, yes? Yes, it's, let's say, it's very nice. It's a compact Hausdorff topological space. For now, in all the examples, actually in most of the examples, it will be a finite topological space. So don't worry. But I introduced the language because it turns out to be a good language if you want to generalize things. So there is a meaningful generalization that we also investigated, and in that case we needed more general topological spaces. But so this is very abstract, but now I show you the examples and you will understand it immediately. So let's start with the most basic example, integer sequences. So the structures are just maps from cyclic groups to the two element set 0, 1. This is the family of discrete structures. These are countably many discrete structures. So what is the sampling process? For every natural number k, the sampling process is that you pick a random element from the cyclic group Zn, and then you look at the k consecutive elements in the cyclic groups. It might go back, but you don't care about that. You get a 0, 1 sequence of length k, right? With this sampling process. If you forget the last component, you get the sampling process sk minus 1. So these sampling processes are forming an inverse system. Now you can consider that inverse limit, the inverse limit of these sampling processes, and if you do that, you end up actually with a probability distribution. This is the limit object on 0, 1 to the z. So this is a compact topological space. You take the two elements at 0, 1, you raise it to z, and you get a Borel probability measure on that compact space, which will happen to be shift invariant. If you look at this space, there is a natural action of z on that, and this probability distribution will be invariant under the action of z. This is a measure-preserving system. And this is basically Furstenberg correspondence principle that you can understand the local statistics of finite 0, 1 sequences using these inverse limits of probability distributions. So is that clear? So this is where ergodic theory starts. This is the starting point, the 0 step. Of course, the whole theory is a big theory, but this is how you start. So this is the first example. Second example is the bounded degree graphs. Again, I repeat everything. We fix a natural number d forever. Let f be the set of graphs with maximal degree at most d. This is so the family of discrete objects. Sampling, what I told you, you pick a random point, you look at the neighborhood of radius k. Now, there are finitely many possible bounded, for every k there are finitely many possible neighborhoods that you can see. So this is a finite topological space. This is the sampling space. And if you have a graph from big F, then the sampling process sk gives you a probability distribution on that finite space. And it is clear that the conditions are satisfied that I told you. There is this sequence between the topological spaces, which are so what are these sampling spaces? Let's clarify. These are rooted neighborhoods, rooted graphs, such that every point is of distance at most k from the root. This is the xk topological space. And you get a probability distribution on this space xk. And you can take the inverse limit of these probability spaces, which will be kind of a space of all rooted infinite or finite graphs of degree at most d. Sorry? Countable graphs. And actually they are connected. So, yes. And so the limit object will be a distribution, a probability distribution, Borel distribution on that space, which I call the general limit object. This is, again, the same principle which Furstenberg introduced. Okay, it's nothing else. This is the same thing. So this limit object was first introduced by Benjamin and Schramm. They proved the beautiful theorem that if you take the limit of planar graphs, bounded degree planar graphs, then it will be recurrent with probability 1. This is a probability measure on infinite rooted graphs, so it makes sense to say that you pick a sample from this probability distribution and it will be recurrent with probability 1 if it's a limit of planar graphs. So let's continue. Dense graphs. So big F, the set of finite structures or discrete structures, is now the set of all finite graphs. And the sampling process is what I told you. You pick k independent vertices, and you create a graph distribution on the vertices 1, 2, and up to k, on the first k natural numbers. You connect I with j if vi and vj are connected in the original graph G. So you get a graph distribution. This is the sampling space. So the limit notion was first introduced by Borcsész, Lovász, Sós, and Vesztergombi. And limit objects were first constructed by Laci and myself. And actually, in this case, there are two different limit objects. One can also introduce that other limit object that I defined you, the general limit object, which is the inverse limit of those probability distribution. And Tao and myself defined that. And there is an interesting thing here, that there are two different natural limit objects. I will tell you a few words about that later. So, few more examples. So here is an example where finite topological spaces are not enough. So let's consider weighted graphs. Fix a number d, a real number, and let F be the set of finite complete graphs such that the edges are weighted by real numbers from this interval. Now, if you look at a random sample, what is this? It will be a weighted graph on k points, which such weighted graphs are forming a compact topological space. So the sampling process will give you a distribution on that compact topological space of weighted graphs on k vertices. Okay, so there is the convergence notion that I introduced, and with Laci we investigated the limit objects also in this case, which actually it's an interesting thing.
The previous example is not a special case of this example?
Yeah, it is. It is. The dense graphs, yes, it is. But I would like to treat it separately because it's already interesting on its own right. But yes. You can also replace the interval minus dd by an arbitrary compact topological space, and you get some interesting limit concept for compact space labeled graphs, which is actually, so it covers many interesting examples. If you do that, that's why we are doing that. Hypergraphs. So, of course, you can generalize the dense graph sampling for hypergraphs, and the sampling process is entirely the same. You pick vertices, and then you look at the spanned hypergraphs. And the limit concept, we introduced it with Gábor Elek, and we proved things about this limit concept using non-standard methods. So this is and also an interesting direction that somehow it turns out that non-standard methods like ultra products help in the subject. But I'm not going to talk about this right now. I want to be more specific from now on. So this was a review of possible limits by sampling. So it turns out that there is a big subject which is the weak limit or sampling limits of discrete structures. Whenever you have these sampling processes, you can introduce limits and limit objects and so on. But now I would like to get back to this nice old case, the dense graphs. And first of all, let me explain the limit object that we defined with Laci. So if you have a measurable function from the unit square to the unit interval, then there is a way of sampling a graph from this. You pick k independent elements from the unit interval 0, 1. And then the random graph model is that you connect I and j with probability w xi xj. So that gives you a graph distribution, a random distribution with graphs where the vertices are labeled by the first k natural numbers. So this is the same sampling space that you have for ordinary graphs. And the theorem that we proved with Lotzi is that if you have a convergent sequence of graphs, then there is a function w such that the limiting distribution of, for every fixed k, the limiting distribution sk of fi is, can be represented in this w. It will be the sampling process from w. Oh, it's a symmetric. I forgot to write. Thank you. It's a symmetric function.
The edges are chosen independently?
Sorry? Xi, the x1, x2, and so on are chosen independently, uniformly at random.
But then after they're chosen, the edges are chosen.
Oh, they are chosen independently. Yes, thank you. That's an important comment. So once again, you can sample graphs from W such W functions, where the sample spaces are the same as for dense graphs. And actually it turns out that you can represent a convergent graph sequence by a W function in this simple way, that the limiting distribution of Sk is exactly the distribution, the k-sample distribution from W. So you are basically representing the sampling this way by a measurable function. This is true. Well, so this is true for every graph sequence which is convergence, but if the graph sequence is sparse, then you get a boring theory. You get zero functions and so on. Yes?
If your original sequence was taken from this model with some sequence of W, so you have W1, W2 corresponding to F1, F2, and so on, will this limit W be the limit?
Yes.
W1?
That's right.
No, but you can
Oh, no. So yes, every W arises as a limit, and actually, if you pick random samples from W for larger and larger k's, they will converge to W in this sense with probability 1. So this is something else that we proved. Now let me introduce graph homomorphisms, which are just a very convenient way of dealing with sampling processes. So let G and F be two graphs. A homomorphism between these two graphs is a map between the vertex sets, such that the edge set of G is mapped into the edge set of F. So in other words, it's a map such that the image of edges is again an edge, but we don't require that the image of a non-edge is a non-edge. Okay, this is called a homomorphism. So the sampling processes Sk can be recovered from the homomorphism density. Homomorphism density. I jumped. We introduced the homomorphism density TGF, which is the probability that a random map is a homomorphism. A random general map from Vg to Vf. And the good news is that the sampling processes, the distributions, can be recovered from the homomorphism densities of small graphs that have at most k vertices. And the way you can recover them is just by simple inclusion-exclusion formulas. Okay, so in other words, a graph sequence F1, F2, and so on is convergent if and only if for every graph G, the homomorphism densities are convergent. in this sequence. This is another way, and this was actually the original way how the 5 people I mentioned introduced the convergence notion. Not by the sampling, but anyway, they are equivalent. It makes sense to talk about homomorphisms of the form TGF, where F is in the closure of the space of graphs. Again, because the sampling process makes sense, so you use the same inclusion-exclusion formulas. Now, we arrive to a crucial point that I really like. So, if you fix a graph H, then you can look at the homomorphism of this fixed graph H in any graph. Oh, I should have written G, the closure of G there. You can evaluate the homomorphism density of H in any graphon. Let's use this terminology. A graphon is an element of the closure of the graphs. Okay, so it's a limit object. And if you look at the homomorphism density in a graphon, then it will be a continuous function on that topological space. And these are somewhat similar to monomials. This is the analogy that we use. And you can also look at the ring generated by these functions on the G closure. So once again, I want you to understand this point, so let me repeat that. There is the closure of the graphs. It's very similar than you take the rational numbers and then you take the real numbers, which as a topological closure. In a similar way, the G bar that I forgot to write, unfortunately at both places, G bar is a similar closure of the graphs as the real numbers are the closure of the rational numbers. So if you have a fixed graph, let's say a triangle, then the triangle density behaves as a kind of a monomial on that space of G bar.
We would say more formally that the real numbers would be the completion.
Completion is a better word.
In many different ways.
Right, yeah. Let's use completion. I like that better, actually. Thank you. No, let's use the completion. Actually, once I decided that, and then I forgot that. But thanks, that's a good comment. So anyway, so the completion.
We can compromise on some cell term.
Now, why don't we use completion? That's a nice word. I like it. So the completion is a nice, compact topological space, and the triangle density is a function on that nice, compact topological space. Okay, so this is, and we kind of think of it as a polynomial function on that space, like a polynomial function on a Euclidean space, right? And you can also take the ring generated by these subgraph densities, the homomorphism densities. This is a nice, really nice ring of continuous functions. This is actually a separating set on that compact topological space. And actually, it turns out very easy to see that the elements of this ring are linear combinations of homomorphism densities. Because taking the product of two homomorphism densities, like TH in some graphon times TH1 times TH2 is the same as the T of the disjoint union of H1 and H2. Okay? And for this reason, you don't have to care about the products. Yes? Sorry? No, I'm just saying that it's an elementary rule, very easy to check, that if you have two graphs and you take the disjoint union of them, then T of the disjoint union in any graphon is the product of the T's of the separate graphs. For this reason, when you look at the ring generated by these functions, you don't have to care about products because they are already included. This is a semigroup of functions already. So you just have to take linear combinations, just the same as when you take monomials. So, but it's worth introducing this formalism of quantum graphs because of this. So let's say that a quantum graph is a formal linear combination of ordinary graphs, like that, Q. And we define the homomorphism density of Q in G with that linear extension of the ordinary homomorphism densities. And so polynomial functions are nothing else than densities of quantum graphs in graphons. Okay? So let's use this form. This is just a language which is convenient to use. So the algebraic point of view, what do algebraics do when they see a ring of functions defined on a space? What do you think? If you have studied algebraic geometry, what would you do? Yes, you look for the zero set. I mean, this is algebraic geometry. You have the Euclidean space, you have the polynomial functions on it, and you look at the joint zero sets for polynomial functions. So let's do that. So study null sets. This is the answer. And the definition, let us call a subset of the completion of the graphs an algebraic set if it is the common zero place of finitely many graph polynomials. And I want to point out, the goal of this talk is to point out that extremal combinatorics in the dense setting is nothing else than the study of these algebraic sets on the closure of the graphs. This is the point that I want to make, and I want to illustrate it with examples. So first of all, algebraic sets can be infinite dimensional. This is the most boring case because the closure G bar, or completion G bar, is a huge compact topological space in some sense, meaning that if you take the common zero place of finitely many graph polynomials, it can be a very big set. As a topological space, it can look like an infinite dimensional topological space or something like that. More interestingly, in some cases, it can happen that that algebraic set that you define is actually a finite dimensional topological space, a circle or an interval or something like that. Or it can even happen that it consists of one single point. And those single points are interesting, because you can't get every element from the closure like that. Not every point is algebraic in this sense. Actually, it's a miracle that there are such elements which are themselves algebraic, because it's such a big space, and if you take the common null sets of polynomials, why would you get just one point? So let's see that. Do you have such things at all? So do forcible graphons exist? Well, there are two very trivial examples. If you say that quantum graph, the edge minus the point in G is 0, or equivalently, the edge density is 1, that defines the complete graphon. That's one single point in the topological space. So this is forcible. This is an algebraic set itself. That's a single point. Or the empty graphon where the edge density of G is 0. That's again a forcible, that's one unique point. But is there any other? No, this is not obvious. Actually, if you sit down and think about it for 5 minutes and you find another one and you can prove it and you don't know this whole story, then you are a very, very smart person. So it's, I mean, it's not that hard, but it's kind of, it's tricky to find any other forcible element, any other point which is algebraic itself. Here are two examples. Both are theorems, actually. If you have let T be the triangle. So if in G the triangle density is 0 and the edge density is 1/2. By the way, the fact that the edge density is 1/2 can be expressed as something is 0, namely again the same thing, that K2 minus 1/2 times the point is 0. Okay, so this is just another way of defining an algebraic set. So with these polynomials, graph polynomials, the set consists of one single point, which is the complete bipartite graphon. So this is a forcible graphon. And this is actually a special case of Turan's theorem. There is another case which is known, which is the famous Chang-Graham-Wilson theorem, which says that if the density of K2 is P and the density of C4 is P to the 4, then G is a unigraphon which can be represented as the limits of random graphs with probability P. Or, if you like the W representation, then this is the W, which is the constant P function. This is one single graphon. In other words, it's a very interesting formulation of this. Randomness can be forced, which is strange because randomness is such a free thing, but here it can be forced. We see it as a single point in this space. And then there is a common generalization of these two facts, which is proved by Laci and Verasors, that step functions are forcible. So what does that mean? A step function is a two-variable function which you get in the following way. You divide the unit interval into finitely many measurable sets. And then the value wxy depends only on the partition sets containing x and y. So it's an object which can be described by finitely many real numbers, the sizes of the measurable sets and the values. And they prove that the graphons corresponding, the equivalence classes of these W's, which are elements from this space, G, the completion of G, are forcible, all of them. And then, for a long time, the whole thing stopped because
the nature of this theorem is a mixture of Turan-type theorem and quasi-random.
It is, yeah. Yes, yes.
And it relies on regularity lemma, or?
The proof is very algebraic. Laci and Vera use graph algebras to prove this. It's a very nice and very algebraic proof. So, yes, but it has a finite version related to regularization. So a step function corresponds to a growing sequence where which has a summary departition of boundedly many, absolutely boundedly many parts. But so there was a long period when we were unable to find anything else than step functions, and we started to believe that only step functions are forcible, which is very reasonable to believe. Let me give you some facts which point into this direction. So a random variable which can be forced by finitely many moments, which is a very analogous situation, has to have a finite distribution. So what does it mean? If you have a random variable, a real-valued random variable, such that its distribution is uniquely determined by finitely many moments, then it can only happen if the random variable has a finite distribution. There is a fact like that.
You just repeated the sentence twice.
Yeah, I mean the distribution is...
You mean a family of random variables. What do you mean a random variable?
A random variable, a real-valued random variable.
Among all random variables.
Yes.
Okay.
So if finitely moments describe the random variable, there is one unique random variable having that finitely many moments, then the random variable has to have a unique, as a finite distribution. Atomic. So this points into the direction that, well, it's a similar context. Maybe it's also true for the W functions. Also, we proved that if W as an integral kernel operator, which you can look at it as an integral kernel operator, has finite rank, and it's forcible, then it's a step function, which also points into this direction. And finally, we also proved that there are not too many forcible graphons in the sense that they form a first category set in the completion G bar. What is a first category set? It's a countable union of nowhere dense sets. Okay, so this shows that it's a sparse set, the set of forcible graphons. Not a big surprise because they can be described by finitely many real numbers. Okay, so it's not a big surprise, but still it was hard to prove.
Is it somehow clear that you cannot force in finite graphs? Are your limits always infinite?
Oh, I mean finite graphs can be represented by step functions. So in this sense, they can be forced.
Is there some simple example of something statistical?
Oh yes, of course. Let's say Wxy is equal to x times y. It can be forced because it's a rank 1 integral kernel operator function.
Okay, so
it follows from the theorem. I don't have any easy proof for something like that. We couldn't, I mean, I haven't seen any easy proof for such a thing. And that's why it wasn't entirely easy to prove that theorem. It's very tricky. Now, but here is the surprise. The world of forcible graphons is full with interesting creatures. So here are two major examples. The first one is a triangular function. It looks like this. This is 1, this is 0. So this can be forced, which is not a step function. And the other example is the infinite lexicographic power of 4 cycles. Oh, sorry. It's a two-variable function. Yes. Yes, so yes, not necessarily, but you can make them rectangles, right? So you divide the unit interval into finitely many measurable sets. Say that they are intervals, but they don't have to be. Then the function is constant on these blocks, Cij, depending on the blocks. This is not a step function, and this is forcible. Oh, now we are talking about symmetric functions, yes. This is symmetric.
The origin is in the upper left corner because it comes from an
I mean, here is the symmetry.
You didn't actually draw the function.
What's the problem? Oh, I didn't do. I drew the opposite. Okay, sorry. Anyways, that's also forcible. Both are forcible. Anyways, good. So obviously these are not step functions. Okay, so this is one example. The next example is very different. It's the infinite lexicographic power of a 4 cycle. What does that mean? You take a 4 cycle on. You take. An ordered power C4 to the natural numbers. And you look at, so this is, I mean the vertex set of C4 to the natural numbers. And then you connect two sequences like that if at the first place where they differ, there is an edge. Okay. Sorry. Let me explain it in words. So you take the vertex set of C4, you raise it to this power, natural numbers. This is a compact topological space. It has a natural probability measure on it. the uniform, like the uniform probability measure. So this is, let's call this space is X. And then you can define a graph on X cross X to actually it's a 0-1 valued function. In the following way, if you have two such sequences, then you look at the first coordinate where they differ. They are not the same. And if at that coordinate the two vertices are connected in C4, then this is 1. If they are not connected at the first coordinate where they differ, then the value is 0. It's a perfectly nice graphon. But actually, I can also draw this. There is a nice way of drawing it. It looks like this is the limit of the following process. You divide a graph, an astronomically big graph, into 4 equal parts, and you realize the 4 cycle between them. Okay? And then you iterate. You divide this again, and you iterate that, and so on. It's a fractal-like structure. Okay? So you iterate this decomposition. So the first example has a real analytic structure in the sense that actually you know that you don't have to use the unit interval when you want to represent such W functions. You can use any other measure space. But to represent the first example, it is the best to use the unit interval with the ordinary topology. So in this sense, it's somehow, I will make it entirely precise, but it has a real analytic structure. On the other hand, the other example has a profinite analytic structure. So these are the two possible type of analysis that can come up. There is the profinite type of analysis, and there is the real type of analysis. And surprisingly, both type can come up here in this world. So yes, I think I explained that. And let me give you 2 further examples. Oh, thank you. One example is a generalization of this example with the square. You can introduce W's which are monotonic in that sense that if so a 0-1 valued function W is called monotonic if Wxy equals to 1 implies that for any pair of coordinates which are both where x0 is smaller than x and y0 is smaller than y, the value is again 1. So in other words, if you draw this W on a diagram, you will get a monotonic curve, basically. It's a very simple looking W. You get a monotonic curve. And if this function is the level set of a 2-variable polynomial, then it is forcible. So it's very algebraic. It has a very algebraic structure. Another example which is more similar to the second one on the previous slide is the following. Let alpha be 3 minus square root 5 over 2. And then you define W to be the disjoint union of a complete graphon of size alpha and the whole W scaled with 1 minus alpha. So this is a disjoint union, the complement of W. So it's a self-similar structure. You take W itself and you take the complement of it, and you scale it to 1 minus alpha, and you take the disjoint union of that with the complete graphon of size alpha. It's an iterative structure again. It is forcible. So now I arrive to something which, this is actually the main point that I want to emphasize in this talk. Otherwise, it is not forcible. This is the only alpha that works in that situation. We have generalized that if you want to use other alpha, you have to. The role is very interesting. The continued fraction expansion has all ones in it. That's the role. All ones, the continued fraction expansion. Anyway, so there is an important point I want to make in this talk, and if you get this, then it was worth giving this talk. So graph limit itself, the theory of graph limits is a measure theoretic subject for the first look. But it has a topological component. And I already gave you some hints about that it has real analytic structure or profinite structure or whatever. It seems to have some topological structure. And I also told you that the theory of dynamical systems is kind of analogous to the theory of graph limits. And you might know that also if you study dynamical systems, topological dynamics comes into the picture. Very special dynamical systems which are also which have a continuous action. Similarly, it turns out that a similar point of view comes here into the picture when you look at graph limits. There is a very natural topological consideration here. Let's start with this simple definition. So if you have a W, a fixed measurable two-variable function, then we say that a function from the unit interval to the unit interval is a typical function of W if for every epsilon there is a positive measure set in the unit interval such that you have that inequality. That basically, let me translate it into words. If you have a W function, a measurable W function, it has rows. And a function is a typical function for W if for a positive measure of rows, they are epsilon close in L1 to that function. Okay? So that means that the W favors, in some sense, that function. Let TW denote the topological spaces in L1 of 0, 1 of the typical functions of W. This is a metric space embedded into L1 of 0, 1. Now here is the nice theorem, which is not in our paper with Lassi, but we actually intuitively use it. It should be written up somewhere. So TW, this topological space, even as a metric space, depends only on the equivalence class of W. It depends only on the graphon representing that W. So in other words, there is a topological space associated, a unique topological space associated with any element of the completion of the graphs. But it can be an ugly topological space. It's not even, in some cases, it's not even locally compact. But let's compute this TW in these concrete examples. If you have a step function, 5 minutes, okay. I think I have exactly 5 minutes left. So if you have a step function, then the topological space is a finite set, is a finite discrete topological space. If you have that example, the first example with the triangle, then you get the closed interval as the topological space. Now in the lexicographic power example, you have the binary tree as a compact topological space. Then in that iterative 3 minus square root 5, I don't remember, whatever example, you have the one-point compactification of the natural numbers. And I didn't tell you the example, but there are examples where you get the circle as the topological space. You can construct a graphon when you have the circle as the base, the probability space, and then you connect 2 points if they are closer than 1/3. So if you look at this example, then you start to believe that. What is the natural conjecture? Tell me a conjecture. These are the topological spaces which came up.
For every compact topological space, you have a forcible graph.
That's also a conjecture, but okay. I mean, yes. So the thing is that these are all compact topological spaces. We don't know if these spaces are always compact topological spaces. This is a topological question. So, question, if W is forcible, then is the corresponding topological space a compact topological space? By the way, let me make a comment about this space W. TW. The TW is a space on which you can naturally represent W. with a Borel measure. So there, it turns out that there is a most natural representation on W on some Borel space, which is the TW itself. So the lexicographic power of the 4 cycle can be best represented on the binary tree in some sense.
Natural. They're all isomorphic.
They are all isomorphic, but
More natural than one translation.
I have a definition, but let me tell you in person. It's nicer if you define it on that space. Anyways, so now here is another question which is very amusing. If W is forcible, then is TW in some sense finite dimensional? By the way, we know only one-dimensional examples in some sense. But in another paper with Lassi, we pointed out that finite dimensionality would correspond to the fact that they have then a small regularization. You don't have to use too many partition sets if you want to regularize them. Only polynomially many in 1 over epsilon or something like that. Yeah, that's a good question. Here we mean some kind of Hausdorff dimension. I will tell you, it's a philosophical question. In any sense you can prove that they are finitely dimensional, it's interesting. Now here is another question. Is there a forcible graph on W such that the corresponding topological space is 2-dimensional, is 0, 1 squared? We even don't know that, but I think it's yes. I have a rough, some kind of approach to that, which shows that that should be forcible. So, and here is a last conjecture. Every algebraic set contains a forcible element. That's a very important conjecture. If this is true, that would say that every extremal combinatorial problem can be extended to another extremal combinatorial problem with more conditions, such that it has a unique solution.
This is when you say combinatorial for extremal graph theory or
Extremal graph theory in the sense that you want to maximize or minimize some kind of function of finitely many subgraph densities.
So this may be true for graphs, but false for hypergraphs.
For graphs now. Let's focus on graphs now. But I think that if this is true also for hypergraphs. And finally, let me close with an interesting example, and this is the last word. This is also forcible. These are an integral operator now is given by the eigenfunctions and eigenvalues. And the interesting fact is that so far all the examples were 2-valued functions, 0, 1-valued functions. So you might think that, okay, the step function conjecture is true in a weaker sense, that at least they have a finite range, but not. This function has a continuous range. A continuous spectrum of quasi-randomness basically occurs. And so this is an interesting exotic example. So thank you very much. Yes?
There is model theory, something called Forcible structures. And recently there has been, so Forcible structures are inductive limits instead of projective limits. You're taking projective limits. The compact spaces define an inverse limit.
Yeah.
And so there is something called Forcible theory and dual Forcible theory in model theory. So if you're ignoring the measure part, then this is already well established and studied theory. I wonder whether you're familiar with this, you're related.
There are problems. I mean, the measures are really important in this theory, in the sense that there is one important sense. You can sample an infinite graph from a W, and if you don't care about the measure, then I mean, up to isomorphism, these samples are like to be the same. If let's say the W takes values strictly between 0 and 1. So as a graph, you don't get too interesting. Anyways, it still might be relevant, so I will look it up. I didn't study that. So.
Is there any other question? So we reconvene in half hour. I don't know. I have to ask the organizer.
Oh, Gábor Elek is the next speaker.